All right, today I'm going to be talking about how to operationalize the inventory management model that we talked about and showed the demo of in the last DAT 40 talk. For those of you, how many people here were in the DAT 40 talk? All right, so a good amount, but not everyone. So I'm going to do a quick recap of high level of what we talked about in terms of the scenario. In that talk, we were dealing with a company called Tailwind Traders. And Tailwind Traders is, how many of you have been to, before I go into that, how many of you have been to any of the other DAT talks today? Okay, so all the same people who were in the last talk. So Tailwind Traders, for those of you who don't know, is a company that does, they are a retail company, and they have a globally distributed business where they have hardware components. And what they want to do is they have this challenge. Their specific challenge is that they have many different stores around the world, and they've done this analysis to see that different items that they have on different shelves, depending on where they're put, affects the end line sales. So for those of you guys who were in DAT 10 this morning, you may have seen that from there we had this data analysis model that we could see that we built that could see point of sales and use that for supply and demand management. And now we can see that there's a direct correlation based on how items are stocked and making sure that items are stocked in the right place and that their ability to maximize revenue. Now the challenge is this: as a globally distributed business with offices with retail chains everywhere from San Francisco to Amsterdam to Tel Aviv, Tailwind Traders has the problem that it's very hard for them to manually manage each of these stores and the individual policies for each of their shelves. Traditionally, the way they've done this is every once a month, every once a quarter, they send to the managers of each of the stores how things should be stocked, where they should be put in the different retail chains, and they hope that the manager goes through and makes sure that everything is implemented. But they don't really have a good way of validating that. And so the way that they validated that is they hire a very expensive investigator service that goes in maybe once a month, once every 2 months, and tries to see are items where they're supposed to be. But just because that's the way they are in that time they visit doesn't necessarily mean it's the way that it's usually supposed to be. And there's a lot of apathy, and it's very, very hard for them to validate that. And so this is based on a real-world use case of work that I did in a previous team with a large company. And we're going to be talking about how we can build a computer vision object detection model using the production video cameras that Tailwind Trader has to validate where items are and make sure that they're in the right shelf, and to be able to put together reports so that we can send alerts to the correct company branch managers across all over the world to make sure that they go through and make sure that each of the items is validated. So in the last talk, we talked about Azure machine learning and the Azure machine learning process. And right now, we're going to quickly review what each of those steps are and how they link to the sessions we saw today. So in the first session that you had in the DAT track was DAT 10, where we talked about how you use Databricks and how you use that to process and prepare data. In the last session, we talked about how you can use different IDEs and the Azure Machine Learning Service APIs to experiment and iterate and build models. And in this session, we're going to focus on how those models work for computer vision. We're going to start very high level, and we're going to get into the nitty-gritty to make sure we understand how object detection works. And we're going to walk through what it looks like what deployment looks like of these models in the Azure Machine Learning Service. And we're going to revisit the demo that I showed in the last session, hopefully now with a new situational awareness of how we can deploy this ourselves. So before I get started, just quick learn alert for those who want to learn more about how you build with PyTorch and Jupyter and Docker and different services. We have at Microsoft this new service and platform called Microsoft Learn. If you didn't see them in the booth, worth checking out. And we have a module that walks through how to get started with these different services, as long as you have a subscription, completely free. So let's take a step back and now talk about how computer vision works. So we'll revisit the MNIST example. How many people here haven't heard of MNIST or weren't in the last session? That's perfect. That means people are learning. That was half and half last time, or I think I saw one hand this time. So for the one person or the two people who weren't in the last session, MNIST is a traditional data set that we use to benchmark image classification models. It used to be the traditional baseline. And essentially the way it works is we have a bunch of images that are grayscale, 28 by 28. And each of these images, this is an example of what one of them would look like. You have the grayscale intensity values. So where it's 0, that's the white. And then you can see what the intensity is of the handwriting. And if I'm looking at this and you're looking at this, we know that this is a 5. But what we want is we want the computer to know that. We want to be able to have a function that I can say get digit past that 28 by 28 scale pixel image, and it will return to me a digit. Now, before we talked about this, but we didn't actually go into how this stuff works. What we're about to do is we're going to start very high level, and we're going to go through a large part of the computer vision landscape. And the first model that we're going to talk about for modeling this type of thing is called the linear model. And the linear model works kind of as follows. We take our image, and again, this is 28 by 28. It's the exact same image we saw here. And what we do is we unravel it. Similar to if you had like a carpet, and you took it strand by strand. And what we're going to do is we're going to take this image and we're going to unravel it strand by strand until we have this one long string, which is going to be our vector, our input. And this is going to be called our input vector. And what we want to do is we want to come up with a model that we can take that linear string. We can then, and it's going to give us some output, transform that string. We'll talk about how we do that in a second. And it's going to get, what we want it to do is we want to transform it into a vector that's indexed 0 to 10. And what we have is we have actual vector, label that the machine can understand. And this label this thing is called a one-hot encoded label. Why is it called one-hot encoding? Well, if you look at the screen here, you can see that there's a 1 in the 4th index. And why is it in the 4th index? Because in computer science, we index at 0, right? So if the 1's there, that demonstrates that this number is a 3. We have our input, which is 758 pixels long for 28 by 28, or whatever, 764. And what we want to do is we want to transform that into a new vector and compare it to our true value. How do we do that? With a basic linear model, we can use something that we do it as follows. We take the input vector, again, the stretched out image, and we multiply it by a bunch of weights that are in the beginning, they're randomly initialized, one for each index, and we just multiply each value. So now what we have is a new output vector of just random numbers. The next thing we do is we add up all these numbers, so we have one number. And then we need a way, this number is going to be big and it's going to be small, or it could be many, many different things. We need a way of putting this number in a scale so that we can fit it between the indexes of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And in doing so, that will give us a new output that can match or not match our given vector. Okay, is everybody with me? Or should I, all right, perfect. Is anybody not with me? Amazing. That is amazing. So essentially, now we get that output value, and we want to compare it with the true value. And the way the machine learning process for this works is we calculate a loss, depending on how close it is, and we go through. In the beginning, remember when we generated those weights, they were randomly generated. Maybe they use some sort of uniform distribution, but they're just randomly weights. So our first outputs aren't going to make much sense. So like in this comic, when I showed the picture of the car to the robot, this webcomic I found, the model's going to say butterfly. But we're going to say it's not a butterfly, and it's not a butterfly by this much based on our loss function. And we're going to use that to update the weight values of the linear model that we multiplied by, so that the next time it sees this image, it will say car. And when we take each of the images, each of the numbers that we've taken in the strand and apply this process, over time, the weights are going to converge into something that helps us represent our numbers, or the images that we saw earlier, as this output vector that tells us what the number is, right? So there can be some challenges in this. When we're looking at MNIST is fairly linearly differentiable, meaning that it's pretty easy to differentiate the difference by just moving this line and updating these weights by adding single numbers and just summing it all up. It's pretty easy to differentiate between whether a 3 is a 2. But there are certain areas where the decision bounds are not necessarily linear. It's very hard to know whether the difference between, let's say, a 3 and an 8, depending on somebody's handwriting. And that's where we get into this problem. So there's a traditional problem called like the XOR problem, and this is where linear models fall apart. I don't know if you guys can see this, but essentially the way it works is, the challenge is this. So imagine we have two classes, and we plot them, and one is 3s and the other is 8. And we have a 3 image here, a 3 image here, an 8 image here, and an 8 image here, and we're trying to update that line to differentiate between them so we know whether a new image is a 3 or 8, and we can't figure out where it goes because there's no linear way to cut that. Well, what we can do is we can actually, if we had a way of taking the inputs and had some sort of intermediate representation, not necessarily from 0 to 9, but maybe from, or as big as the 700-ish vector that we had in the beginning, but something like 228, we might be able to change the representation space so we can actually differentiate between these two. And so the way this works is this is how nonlinear models and feed-forward models work. So instead, think about it this way. Instead of me doing a direct operation from that image of a number that I turned into a strand, converting that into something and making the direct prediction, instead now I'm coming up with some sort of intermediate representation and using a hierarchical set of patterns and many different kinds of these to be able to get a number that can differentiate between situations where I have nonlinear bounds between my classes. So that's great, and that actually helps us. We can train really, really strong MNIST models on that. You could get high 88% accuracy, pretty strong recall and precision. But the challenge is, what do you do when you have more complex images? And for a really long time, it becomes really, really hard because, for instance, if I have an image with that's 5 megabytes or a couple of megabytes, or there's a lot of detail in the image or a lot of referential detail in the image, it's very hard to really understand where those bounds are, even with a linear model. It's very hard to know how big that intermediate set of weights should be and how can I actually represent that information. And for a really long time, when we think about this, the computer revolution, that vision revolution that we talked about in the last session, that was one of the biggest bottlenecks that we had. It was really hard to get around this. And the way that we traditionally try to get around this when it comes to classifying the difference between whether there's a bird or a cat or a dog in an image is we would handcraft what we called feature extractors. So imagine I start out with a source image like this. I would come up with a matrix that would do something like strengthen the edges and zero out everything that's not an edge. I would apply it using a pattern called a convolution over the original image, and out would come a new image that has just features that represent just the edges. And now when I build my model, what I would do is I would take this output feature, or this edge features, and I would use those edges as my input instead of all the complexity of the original image. So I'm going to quickly give a demo of kind of what this looks like from a coding perspective so that we're all on the same page. So I have here a list of kernels. And essentially, we take our image, I load it up, and we define this convolution function. Again, all that does is it takes this filter and it runs it over the image in a pattern and brings us out with new values that strengthen or weaken different parts of the signal so we can have a new, it serves as a feature extractor. Sorry, 1 second. And we will define this filter here. And I'll take my original image, so like this image of the fence, and when I apply the convolution on the image, I get these new features. So this is great, but the challenge is it's really hard to come up with strong features that help us differentiate between complex image classes. And so when you're thinking about this traditionally, like when we're coming up trying to differentiate between cats and dogs, it can be really, really hard because just the edges of, just having the edges that might make things a little bit easier than just look at the raw image, but it's not enough. And the key insight that helped, combined with advances in computation that helped us get to where we are today, was the idea of what if we could, instead of hard coding and coming up with different mathematical functions and transformations for these feature extractors, what if we could learn them? So now, instead of learning a direct transformation of our entire image as that linear strand, instead we're going to learn this small matrix that is our feature extractor, or our filter. And that's where this concept, if you guys have heard of the convolutional neural network and you've always wondered, what's a convolution, what's a filter? That's essentially what's going on here. At the end of the day, a filter is a learned feature extractor. And essentially the way we do this is we learn in the same way that we did those same operations to transform our original image to a output representation. We do that for now, instead of for the full image, for our filters. And there are different ways that we can apply the filters. So essentially, we can put padding around the filter, and we can convolve with different padding. And sometimes we can also put gaps out, and that sometimes helps for different operations. And we can also use the information of the filters, and we can pool this information so we have a more dense representation of our data, and we can actually get better hierarchical features. And the way this works is essentially we take the same pooling mechanism that we talked about before, and there are usually 2 different methods for this. One's called max pooling, the other one's called average pooling. And what we do is we take all the outputs in average pooling, and we just average that number, and then we put it in the corner of the output. And when we put this all together, and we take our input image, and we do our convolution, and then we do our pooling to have a more dense representation of it, as you can see over here, or for people on the other side over here, right? As we do this at each layer, what ends up happening is we start learning hierarchical representations of different features of the raw image that help us make better classifications. And we can actually transfer this, which was the big innovation. I can train a model like this on millions of images like ImageNet, and then because I know that these, well, I don't know, but because they tend to be the earlier representations tend to be lower level, like edges and lines, I can actually use those in models from different domains. So this helps us understand what changed and how image classification became viable, but there are some challenges traditionally with just using convolutional models for something like validating where certain items are on a shelf and making sure that they're stocked in a certain order. What's the challenge? Well, convolutional models struggle with ordering. So for instance, if I have an image and I know that 2 items that I can tell that there's a dog in the image or a cat in the image, but if I want to know the dog's left of the cat, or the cat's left of the dog, I would struggle with that. And when we're doing stuff like validating the policy of a bunch of items on a shelf, we're also going to struggle with that. So that's why in this case what we'll look at is we'll look at object detection. What object detection enables us to do is if image classification tells us that there's a cat in a picture, and localization tells us the bounding box of where that cat's in the picture, object detection tells us the bounding box of all the different cats in the picture, all the different dogs in the picture, all the different little ducks and everything. And you can actually even go one step further. There's another field on top of this called image segmentation. But the trade-off there is it becomes a lot more complex and a lot more expensive to annotate. So that's great. How do we get started with object detection? We saw image classification. We kind of understand that. Well, I'm going to give a brief history of how this field transformed from where we were with image classification to building object detection models. And the first thing we're going to look at is a tool that I built in my previous team called the Visual Object Tagging tool. And what this allows you to do is this allows you to annotate images, because in order to build object detection models, we need more than just that one hot vector that tells us what class something is. We actually need to know what the actual bounding box is around the original object. So traditionally, that was a very expensive thing to do. But some of the things that we've done at Microsoft is we've built tools that use active learning and different mechanisms that allow you to quickly annotate and build very, very accurate data sets that you can use to generate custom models. And what's really nice about these tools is when you export, you can export the models directly in the formats that you need, whether that's TensorFlow for Pascal VOC, whether that's YOLO, whether that's TF records, whether that's pretty much any model format that you need to get started with object detection in those frameworks. What does that enable me to do? That enables me to go, if I want to go to TensorFlow now, or PyTorch, as we're going to do, and build my own YOLO model, to go, what's the tutorial for doing that? Delete the directory for detecting cats and dogs, because we want to detect items on a shelf, and replace it with my folder, and then just run through the tutorial, and now I actually have a model that's related to my data. So those are the types of things. Now, if I don't necessarily want to go through the whole process of training out a custom object detection model on these platforms and using these frameworks, I can actually use this service directly with the custom vision service and the cognitive service tools that you learned about in DAT30, and the tool will directly integrate with that. And what's really nice is there's some awesome features that are being developed right now that enable things like very, very quick segmentation annotation and the ability to take a model that's already been trained and run it to help me annotate better. So this is the first step. The first step is generating these data sets. Now imagine that I've gone and, as you can see, annotated a data set of the items on the shelf. How do I actually use that data to get from my image classification model that we had earlier to the object detection model? So the earliest way that we would try to do this is we used what's called a sliding window approach. And it's pretty simple. Essentially what we do is we take a little box of different dimensions, and we drag it over the image, and we run our classification model. And we say, is there a person, for example, here, is there a person in this box? No, slide it over. Is there a person in the box? No, slide it over. Now you can imagine that that's very slow, number one, because we have to run this model, again, over different sliding windows. And the other real challenge with it is it's very hard. Objects come in of the same type and class come in many different sizes and shapes, depending on lighting, depending on camera angle perspective, depending on the item itself. So it's very hard to get a bounding box that scales well for all different types of appearances of a given object. So how do we find regions of various sizes and shapes? Well, this is where we originally started asking these questions. The first thing that we did was we used what was called a region proposal, object detector. So the way region proposal object detection works is, or used to work, is essentially we would do something called selective search. So we would essentially segment using colors, like a histogram of colors, or trying to see exactly where the most popular colors are and what the boundaries are. And we would use that to figure out where the area of greatest shape is. And this would give us a bunch of potential places where an object could be. And and essentially what we would do is then we would take the item there, and we would scale it and pass it through the image classifier we had. And now instead of having to go through a window of each size, we just test each one of these boxes, and based on classification accuracy, we would know that there's an object of a given size or shape in one of these boxes, right? But the challenge with this is, again, it's very, very slow. Plus, you have this whole overhead of having to do the selective search. So one of the ways that they sped this up, the first big improvement from the neural age, when we're talking about the computer vision revolution, was this algorithm called fast RCNN. And essentially what they realized here is instead of taking all the image features that we have at the start of the model, when we just process the image, what we can do is we can actually do the selective search. And when we start our classifying of the model, we should classify only the features that we've extracted. So what does that mean? Well, if we go back a little bit, you remember this image here where we have this object, like a car. Instead of making the classification detection here 100 times for each one of those boxes, we do it here at this line. And for those who are on this side, it means instead of here at the key object, we make the detections at this phase, and we just run the selection algorithm at the top there. And that sped things up. That started making this stuff more viable. But again, still very, very slow. That turns it from being able to do, taking an hour to do an object, to get all the objects in a populated image, to 5-10 minutes, but it's not what you see today, right? So the next big thing that helped us bring it one step further was this concept of faster RCNN. And the big thing that changed here was this removed the concept of selective search. Instead of us having to use a standard algorithm, instead we tried to have an extra model and use what's called multitask learning to learn exactly where an object could be. And then once we knew that, we could then classify the object. And that sped things up and started making it very, very viable. And currently, when it comes to the state of the art for what's called region proposal networks, at the time of the creation of this deck, RetinaNet is one of the models that allows us to do this very, very accurately for object detection, and also pretty fast. And we're going to talk about this a little bit later in terms of the trade-off when we talk about the actual model that we used. Because what happened was, around the time, right before the time where we got the faster RCNN, there was a split in terms of the techniques that were used for object detection. And the split came with this concept of what's called a single-shot detector. What is a single-shot detector? Well, before, in a region proposal network, what we do is we come up with a model that tells us where all the regions are where an object might be, and then we run our classifier on those regions, right? In a single-shot detector, and you guys might have heard this term before if you've done computer vision, what's changed is when we make the prediction, we predict both where the object is going to be and the object class at once. And this is where the concept of YOLO comes in. Essentially, you have this image here. You break it up into different regions, and in each region I can make one classification one prediction of potentially where the bounding box is. And based on the overlaps of where the center of the object might be, then I get this box, and I get the class label for that there's a person or a basket in the person's cart. And the reason I bring this all up in terms of everything when we're talking about object detection in these two different methods is there's a trade-off between them. And the major trade-off is this. It's precision versus speed. So if you look at something like YOLO V3 here, which is the model that we're using because we have a video camera and we want to be able to see very, very quickly and very fast how well this model, how well the stuff on the shelves is being classified, we can see here that we can evaluate with 31 mean average precision score, which is pretty strong, very close to state of the art, with 29 milliseconds. But with the region proposal models, we can get 37.8, which is much larger and much more accurate mean average precision, but the evaluation time there is 198 milliseconds. So again, the reason I bring up these two types of mechanisms when we're talking about object detection is like in any model or anytime you see big flashy benchmarks and everything, understand that there are trade-offs between the different architectures that you might use. So that brings us all back to where we started. We now understand a little bit better from image classification to object detection how the model that we've built for Tailwind Traders works. Now let's actually look at how we deploy this model using Azure Machine Learning. And so there are a couple of steps that you need to take once you've trained a model. And the first is that we need to register the model with the service. So essentially, we take the model that we've trained, we store it in Azure Blob Store, or locally, or wherever we want. We register the model using the command model.register. We provide the path, and that allows us to register a model in the Azure Machine Learning portal. So if I go to the Azure Machine Learning portal, you saw the experiments in the pipeline and the compute from the previous one. Now I can register my model, and I can see this model and some information about the location of the model, and I can now deploy from this. The next step is I need to create an image. And the way an image works is the model gives me the weight values, the things that I learned that I need in order to make a prediction. But that alone won't actually allow me to do anything, right? I still need the code to be able to take the image, pre-process it so the model can understand it, take the output, and then process that so that I can actually make my prediction, to process and understand what my prediction means, right? So in order to do this, you provide two simple things. One is the location of the model, the ID of the model that we just registered. The second is the scoring file, and we'll see exactly what that looks like in a second. And the Python environment of all the packages for all the dependencies of the frameworks that we're using. So for instance, if I'm using TensorFlow, I define that in my environment file. If I'm using PyTorch, I define that in the environment file. I provide the scoring model file that evaluates, and we'll show you exactly what that looks like in a second. And we provide a reference to the model in my model store. And then we bundle that up in an image, and we can deploy that. So this is the example of the scoring file and the environment file. I'm going to show you a specific one that I built for this demo. And again, all this stuff is open source. If you have a challenge finding it, feel free to come find me tomorrow at Meet the Experts or tweet at me, and we'll get it resolved. So essentially, before we saw that there was the train script that we used for training models in the last session. And in this case, we have our scoring script. So here I have a couple different packages, such as PyTorch, PIL, used for image processing, scikit-image, also used for image processing. And all I have, and essentially what I do is I define the pre-processing code. I load and the code for loading the model. And the run script for actually running, taking the input data and making my prediction. And essentially what this is doing is it's the same standard code that I would find if I looked at any GitHub example of a YOLO object detection model, right? And I define a couple helper functions. And all I have to do, and I validate locally whether it works. So essentially, I have my output run something that takes an image and will show me what the output value of the image is. So let's take a look at this actual experiment and how the code looks for actually registering this and submitting it. So okay, so this is the running experiment. This is the evaluation code. And I'm going to pull up very quickly what the code looks for deployment. Perfect. So okay, so essentially exactly as we did before, we pull in Azure ML. We load our workspace from config. So I'll run these two things real quick. We pull the model that we've trained. This is the code that we use for registering the location that holds the model. And we use this to manage the environment of everything that we need for our image. So again, very simple. It pulls from our configuration file, and that's locally here. You can just look at that. It's just a list of the dependencies for the Python version, the pip packages that I need, maybe a Conda environment if I have other dependencies. And this enables me to create my image. And then I add any local dependency directories or scripts that I have in addition to this. So for instance, like models.py, which is a piece of code here which has helper functions for my model that I've trained and built. And utils, which is additional utilities. And then from there, I can just create an image with that. And I push that image to Azure Machine Learning. And if I look at my images now, when I've pushed that image to Azure Machine Learning, I can now drill into that image, and that's hosted in a way that now I can deploy this image. And there are a couple of different ways that I can deploy the image. So at this point, we have this image, and we want to deploy the image. So again, the image was created by putting together our model with a scoring file and our environmental dependencies. We have this image, and there are three ways that we can deploy this. One is using AKS, Azure Kubernetes Service, which allows us to, if we're submitting this image for something that we want to scale, it handles all the scaling and the managing of the service in a way that we can distribute at scale and make it localized across the different distributed centers that Tailwind Traders has. Or if we're just doing basic experimentation, we can deploy as an Azure container instance. And there's also a capability for on-the-edge deployment as well. So to deploy the image, very simply what we do, we'll look at the ACI example. We just define this code around an ACI web service, and we create a deploy configuration that tells me what's the computational resources I need for evaluating this model. So for instance, I need 1 CPU core, and I'll give it 2 gigs of memory. And then we just write this command that takes web service deploy from image. We provide it the ACI config that we just created above, and the image, based on the image that we defined in the last step. We give a name to it, and we provide the workspace. And what that will do is that will deploy the image as a service. And so if we look at our code, that's this step, right? So we give it a tag, we describe it, an object detection model, we deploy the image from the web service, and this will give us a scoring URL that then we can evaluate against. So if I go to PyTorch, if I go here, I can now go to my deployments, and you can see I have these different endpoints from when I deployed this image earlier. Great. Okay, so now we have that. Let's go to the next step. The next step is from deployment, what we want to do is we want to actually evaluate the image. So I'm going to do this, and I showed a high-level example of this before. We define a function that takes an image, opens the image as a byte stream, and we'll draw on the image what the bounding boxes are once we classify from it. We give it our service endpoint, and we load this image. So last time I showed this example. Let's try a different one now. So let's try, I'm going to show you kind of what the next image in real time. Perfect. So we'll have this new image now with a bunch of different cups and plates. And what we're going to do is we're going to take that image, we're going to pass the image URL, we're going to pass this confidence threshold saying that for a bounding box to appear, it should have at least 0.2 confidence. And we're going to get the response back in JSON from our service. So you can see we got a 200, which means that our response worked. And what we're going to do is let's print out. Let's see what that looks. So we see that there's a cup at this index of xy with a height and a width and a high confidence. And we can see that the model gave us back our responses. And we can actually visualize this, right? So we can see here the individual bowls, the cups that were found. And there's also, we can see that there are certain areas where we can improve and build and iterate on the model. But we can see that we have a model now that we went very, very quickly from with a couple lines of code from having a model that we trained to a model that's now on a service online with ACI that I can evaluate. And with a couple extra clicks, I can deploy it as an AKS model. And I can scale that model out with very, very little additional configuration. And if I want to go one step further, I can even deploy that model to run on edge devices. So with that, I'm going to quickly recap everything we talked about. So hopefully by this time in this session, we talked, and today, based on the last two sessions, we've talked a lot about how computer vision works, kind of giving more context in terms of how these algorithms work, how to work with Azure ML models that we trained in the last session, how to set up the model in the scoring files, how to take the models after we've deployed them to Azure Machine Learning Service and wrap them in Docker images, and then how we can actually interact with those images in REST to use for our own computer vision applications. So again, everything I talked about today is here in the GitHub repo on aka.ms ignite the tour. If you have any additional questions, I'm available after. And I want to thank you again for coming.